Hello, Stats class. Here is the beginning of Chapter 10. So exciting. So we are going to be shifting to comparing two different populations, starting with proportions, and then we'll go to means in a bit. But we're going to start talking about what if we have two populations, which means we're going to take two samples from those populations. We're going to calculate the proportions for those two samples. And so everything is 2. It's kind of crazy. So the first thing we have to do is, now that we have 2 of everything, we have to get used to putting subscripts on our variables. So instead of P, we're going to call it P1 and P2. And subscript means those are lower instead of up high like an exponent. So those would be our two population proportions. And remember, some books use pi for this, but we're using P. The sample proportions would be called P1 hat and P2 hat. And it's pretty predictable that we would want to do this, but I'm just making sure you are prepared for that. And then, of course, we'll have sample sizes, which are N1 and N2, because they might not be the same size. So those are our sample sizes. And I could keep going. I could talk about Q1 and Q2 and Q hat 1. And I'm not gonna write all that down, but it also exists. So what we're mostly going to be interested in is comparing by doing a difference, or in other words, subtracting. We want to know the difference between our populations or the difference between our proportions. Let's start with populations. So if we want to know, like for instance, is one population more likely to do something than the other, that word difference should remind you that we're subtracting. And so we'll get to review a little old stuff today, which I kind of like. This is actually part of what I like about Chapter 10, is it includes some review from Chapter 6. Ooh, that seems like a long time ago. December was Chapter 6, which was about random variables. And it includes some review from Chapter 7, in which we did in January, which was about sampling distributions. And so we're going to review that stuff before we do the inference. So we are going to also combine it with some of the stuff from chapters 8 and 9, not till the second lesson. So in lesson 10.1b, we'll get to that. For today, we're just going to talk about this stuff and how it applies to the differences. So I'm going to teach you what is true, some properties of the sampling distribution. Of the result of subtracting two sample proportions. So that's if you do P1 hat minus P2 hat, what happens? So I just want to remind you from chapter 7 that sampling distributions means you take these two populations, you take your two samples, you find your two proportions, you subtract them and plot it, and you do that over and over again. So we're talking about many samples from our two populations, find the differences of the two proportions, plot them, and see what the distribution looks like. So we're going to talk about the usual 3 things, shape, center, and spread of that distribution and what we can do with it. And then we will come back to how you predict the population proportions from that. Right now, we're just focusing on the sample proportions, what's true about those sample proportions. So we hope that the shape will be normal, don't we? I mean, it'd be really nice if it were normal. It'll make our calculations so much easier. And that is true in a certain situation. So I'm going to just say it's approximately normal if. And what we need is for both of these populations to be approximately normal. And it wouldn't be the populations so much as it would be the two sampling distributions, so of P1 hat and P2 hat. So I'm going to say if both sampling distributions, let's put a little thing there, distributions are normal. If you take two normal things and subtract them, you get normal, which is kind of nice. And that would be the sampling distributions of P1 hat and P2 hat would both have to be normal. So if you're trying to check and see if this is true, you would check it the same way we've done before, which means you're going to do NP and NQ, except now there's 4 of them. That's kind of bad news. So we're going to check N1, P1, and N2, P2, and N1, Q1, and N2, Q2. Now we've seen before that sometimes you use a hat on this and sometimes you don't. If you know the population value, you should use it. And if you don't, you'd put a hat. So you'd replace it with P hat if you need to. P1 hat. And you do the same thing with all 4 of them. So if all of those are, I should have finished my sentence here, sorry, all greater than or equal to 10, then you can assume that the sampling distribution is approximately normal. And you probably could predict that we're going to have to check that on part of our 4-step process, which we're going to get to. So that's normal if this is true, and that kind of should make sense. The only hard part is there's 4 of them, but that's okay. We can handle 4 of them. Center. Well, if we were in class, I would ask you, what do we hope is true about the center? We hope that the center is unbiased, right? And unbiased means, let me write that here. Unbiased means that the mean of the P1 hats minus the P2 hats, oh gosh, so if you take all of these sample proportions and you subtract them and you find the difference and you plot them, we're hoping that the center of that plot is the same as the difference in populations, which is P1 minus P2. So that's basically what we're hoping will happen. That would mean that this is an unbiased estimator. And that will happen if we do our sampling correctly, if we have random samples. And in this case, there's 2 of them, 2 random samples from 2 separate populations. That's exciting, but other than that, it's the same check as we usually do. This is another one of those statistics that is used often because it's naturally an unbiased estimator. So that's good. In graduate school, I had to prove that. You don't have to prove it. You just have to believe me when I tell you. All right, spread. This is hopefully starting to sound a little familiar. We're doing the stuff we did before. We're just doing it with 2 different things. And same thing happens with spread. We're going to talk about the formula for sigma P1 hat minus P2 hat. So if you take the standard deviation of all of those, some books put a parenthesis around these, and maybe that would be more clear. So the spread is based on, here I told you we were going to review random variables, right? We talked about if you subtract 2 random variables and then take the standard deviation, that's that formula that looks like the Pythagorean theorem. So I'm just going to remind you of the Pythagorean theorem formula. It is a plus, even though this is a minus. Pythagorean theorem of statistics. That's what it's sometimes called. But then what goes in those parentheses things? Let's think about that. It would be the mean of this one, and then, or not the mean, the standard deviation of this one, and then the standard deviation of that one. So it'd be standard deviation of P1 hat and standard deviation of P2 hat. And both of those get squared and added together and square rooted. That's the chapter 6 review. But then in chapter 7, we learned what these were. So we could replace them with the, basically this one is P1Q1 over N1, and that whole thing was square rooted, but then we're squaring it. Oh, that's interesting. Oh, that's N1. And then this one, the thing in that parentheses is P1 or P2, Q2, also square rooted over N2. So this piece is from chapter 7. And then notice that the squared and the square root, they cancel each other out. So we can simplify some more and make it into the formula we're actually going to use in this chapter, which is P1Q1 over N1. Leave off the squared and the square root, and then do the same thing with 2. It's a little bit messy, this formula, but this is the formula we're going to be using for the rest of 10.1 for sure. This is the official formula. I'm putting a box around this version because it's the one we're going to use. This is just showing you where it came from, and then this is the one we're going to use. Star by it or something. Now, when is this true? Now, we talked about this way back in chapter 6, and then we mentioned it again in chapter 7. This formula works if we have independent random samples. Oh, that sounds familiar. Normal, random, independent, right? We've seen those before. So if our random samples are independent of each other, and if N1 is less than 10% of the first population, and if N2 is less than or equal to 10% of the second population, all of this has to be true to make this formula work. Well, most of the time that all is going to be true and it's not a problem, but it's something to think about. We have two 10% rules to check now. Plus we have this, are the samples independent of each other? For instance, if you take a random sample and everybody in the, like say you have a random sample of men versus a random sample of women. Well, if the women happen to be sisters to the men, and brothers, yeah, if it's sisters and brothers, then maybe they're related somehow, and so then that wouldn't be independent random samples. So you have to be careful about that. So all of that is the theory behind all of what we're about to do in chapter 10. So it should sound very familiar. Shape, center, and spread is tied into the normal condition and the random condition and the independent condition. We're still doing those. It just got a little more complicated. So what are we going to do with this? The first thing we're going to do with this, and then we're putting off some of it until the next lesson. The first thing we're going to do with this is if you know some population information, we can do calculations of probabilities based on that, and that's not even inference. That's stuff we did in chapter 7. And so we're going to do some of the stuff we did in chapter 7 now, again. Chapter 7 stuff, before we get to going the other direction. So later in lesson 10.1b, we will talk about what if you know the sample info and are trying to predict the population. That's coming later. Right now we're saying, let's say we know the population. Let's say we know, for instance, that P is representing the proportion of students who do their homework often. Are you in that proportion? I hope you are. I wouldn't say I have to do it 100% of the time, but they regularly do their homework. All right. And let's say our two populations are Cascade High School and Mariner. I'm going to say Cascade is better than Mariner. I'm prejudiced, I know. I'm going to, instead of using P1 and P2, I'm going to call it PC and PM because it makes it really clear that that's what I'm talking about. I don't have to, now I won't have to remember that the first one, that one refers to Cascade because C is obvious. So let's say, I'm just making up these numbers and they're probably not true, but let's say the population proportion of Cascade students is 57% that do their homework regularly, and Mariner only has 38%. Now, like I said, that might not be true. I might be dissing Mariner, but you know. So then, suppose I take a simple random sample from each school. And so I take, because I want you to know that they don't have to be the same size, I'm going to make my number that I get from Cascade be 100, and I take a sample of 200 from Mariner, because, you know, they don't have to be the same size. And I'm going to find the probability of a sample difference greater than or equal to 30%. So let's think about that for a minute. We've got our normal curve, picturing in our mind. The center is the difference between these. So if I do PC minus PM, that would be, comes out to 19%, or 0.19. That's the center. In a minute, I'm going to calculate my standard deviation, which is how far over it goes, right, till that inflection point. So we'll get to that in just a minute. But remember this conditional probability thing? We're finding the probability that the difference in P hat C minus P hat M, probability that that difference is greater than or equal to 0.3, given that the true difference is the 19%. So that's what we're about to calculate. And we would need to do this standard deviation and all of that good stuff. And we're going to find a z-score. That's where we're headed because it's a normal curve. So let's find z. Let's remind you that z is always the sample minus the population over the standard deviation. And so my sample value, that's the 0.3. My population value, that's the 0.19. And then I haven't calculated standard deviation yet, so I'll do that in a few more steps. It's this kind of messy formula. Actually, I really like that formula. I don't know about you, but you might not like it until you get used to it. It's okay. So I'm going to write out the formula as PCQC over NC plus PMQM over NM. That's, if you didn't need to write that out, it's okay, but I wrote it because I wanted to make sure you're clear that that's what I'm using. I'm using that formula. Let's go ahead and subtract the top. It's 0.11, 11%. Let's start plugging numbers in down here. So I'm going to show lots of work just to make sure that you're with me. So then this would be PCQC. PC is 57%. 0.57 times QC, which is 1 minus 0.57, that's 0.43. And then NC is the number from Cascade is 100. And then I'm going to do the same thing with the Mariner numbers. I'm going to use the 200, and I'm going to use the 38%. And I'm going to do 1 minus 38%, which is 62%. And if you need to write that somewhere so that you know what's happening, that's what I just did. And I did the same thing to get the 43. Okay? So then I get out my calculator and I type all of this. Parentheses are important when you type all of this. So I'm going to demonstrate that you can, actually you could type all of this stuff underneath first and then come back and square root it. That's probably a better way than doing it all at once. So 0.43 divided by 100. I don't need parentheses for this part because the calculator knows to do this multiplying and dividing first. 0.38 times 0.62 divided by 200. That's the thing under the square root. Wait, no it's not because I typed a negative instead of a decimal point. Let's do that right. I did it again. That's so funny. Okay, that's the actual thing that's under the square root. I'll write that down, 0.003629, and then I'm going to square root it, and then I'm going to divide it. So I'm showing more work than I normally would for you. Hope it helps you. Square root answer, 0.0602, and then when you divide 0.11 divided by that, you get 1.82, round it to 6. That's my z-score. Great, I found a z-score, hurrah. Now I need to find the probability. So I want this probability here is the same as the probability that z is greater than or equal to this number. And so I've used both of these to find my z-score, and that's why I could just write it the simpler way. And that's a normal CDF or a table A. 1.826, 999. I forgot I should probably do this. This was 0.06, and my z-score is just over 1, so it's like about here. finding this probability. So that's the shaded area that I'm finding, and when I type that, second bars, normal CDF answer, and 999. And I got 0.0339, which is the probability, or about 3.4% chance of getting this sample result, or more extreme, if this is true. That kind of sounds like a p-value, doesn't it? Yeah, that's what we're doing. We learned basically in chapter 7 how to find a p-value. You just didn't know it was called that. That's amazing. So that is the beginning of chapter 10. We're not doing inference. We're saying we know the population, and we're going to find a probability of a certain sample value. And then guess what? In 10.1b and c, we will go to the inference part, and that's coming in the next set of notes.